Hello everyone. Today I will talk about our recent research toward a quantum thermodynamic precision advantage in a superconducting circuit. So this will be the first experimental talk of the session. And the experimental part of the work has been performed in the group of Simone Gasparinetti at Chalmers University of Technology in Sweden. And we have been collaborating with the Trinity College Dublin together with Mark Mitchison and his student Kalak Madavia. So when talking about precision in microscopic type systems, it becomes important to think about fluctuations in a current, for an example. Because at this scale, the variance of said current will lie on about the same level as the mean of the current. And as an illustrative example, we can look at a continuously monitored quantum system where the output current can be either in the form of quantum jumps or of some diffusive type current. Gathering this data, we can then build up statistics, which then relates to the fluctuations of said current, but then also, of course, the mean. And this type of stochastic type dynamics we find all over nature. The ticking of a Brownian clock is an example, the workings of many biomolecular processes, heat transport in heat engines and refrigerators are another example. However, what they all have in common is that we can't engineer or find these type of systems with arbitrarily low fluctuations in them. Because of something that we have heard of today called thermodynamical uncertainty relations, or TURs, where I've written up the one in its original form here. We have the noise of the system D over the mean current, and this quantity is then bounded by the entropy production of the system. But as it turns out, we can actually violate this bound, but by utilizing quantum mechanical resources, which has also today been shown in some examples. And another such example we see here, where Calais and co-authors describe a quantum three-level system that couples to two thermal reservoirs, a hot and a cold one. And by studying the heat flows into these reservoirs, we see that we can in fact violate the TUR. So this is what we actually want to build. And we work with circuit QED, so superconducting qubits and microwave photons is our bread and butter. So what we want to do is build a quantum heat engine, put it on a chip inside of a dilution refrigerator, and then measure the heat flows and the fluctuations of these heat flows. And here I have to emphasize that because we're dealing with microwave photons, we can't simply put a microwave photodetector at the end of our readout line, because as of now, no such thing exists with enough efficiency, at least, to get the statistics that we want. So how do we do this? Well, of course, first of all, we need to build the device. Then we need to operate it as a thermal machine, and then measure the currents and the noise of said current. So with that said, let me introduce you to our device. It is composed of four main parts, and the main one is the two flux-tumal transmon qubits that we have coupled to each other. These are marked in green and purple over here, and together they form a hybridized energy level structure with the first excitation manifold showcasing an antisymmetric state and a symmetric one. Secondly, we also have a dispersively coupled readout resonator, or a harmonic oscillator for those of you who would prefer that. Through this resonator, we can either read out the state of the qubit, we can also coherently drive the 0 to A transition, and it also serves the purpose of protecting the A state so that it does not decay too quickly. Then we also have two separate flux lines that couples longitudinally to our two bare qubits. Through this, we experimentally usually use them in order to tune the frequency of our qubits. However, in this case, we use them in a different manner, because now we're actually going to send in spectrally localized white noise centered around the frequency that bridges the gap between the antisymmetric and the symmetric state. And what this actually does is that it's open up a channel between the antisymmetric and the symmetric state through which we can incoherently swap excitations. In essence, we can go from a pure state of A into a mixed state of A and S. So the dephasing channel here actually acts effectively as an infinite temperature bath. So there we have our hot bath. Our cold bath is then realized with a waveguide, which we can view as a physical cold bath that supports a continuum of modes, and in our case, it stands at around 45 millikelvin. And into this bath, the symmetric state can then decay and emit a photon. And this is then the operations of our heat engine, our thermal machine. So how do we now demonstrate how this device actually works? Well, of course, we would like to measure the emission of these photons into our cold bath. So in order to do so, we coherently drive the 0 to A transition. And without dephasing the system or doing anything, we then study the power spectral density of the output field coming from our cold reservoir. And when we don't send in any noise, what we see is nothing, as expected. But when we then turn on this incoherent channel between A and S, what we see is then the emergence of a peak in the cold bath, meaning that we now have an influx of photons, thus the operational regime of a thermal machine, or a heat engine, if you want to say. So this is a PSD type measurement, meaning that the integral of these bumps that you see would correspond to the actual heat flow into our reservoir. So how do we then measure that? Well, to this end, we turn to the integrated power of our signal. This I here depict as Q, and we integrate this power during some time t in experiments. We do so for around 3 microseconds. And then we measure the quantities Q and Q squared when we operate the device in the on mode, meaning that we have dephasing and we have the coherent drive. Then we turn it off, we turn it on, and we repeat this many, many times. And we do so in order to gather statistics to get the expectation value of Q when the device is on, as well as the variance, and then also the same quantities when the device is operating in its off state. So we do so, and the result is as follows. Using input-output theory, we can actually relate the measured quantities here to the average current J. And we see that the experimental values coincides very well with the predicted heat flows that we can calculate from full counting statistics. And we note here that because we can measure heat flows, we can also determine the entropy production of our system. Because we know the temperature of the cold bath, the hot bath is effectively at infinite temperature. So that's directly 2 quantities we need to determine the TUR. Then comes to the current fluctuations, the hard part of this setup. Here, D, the diffusion coefficient, or the noise, is related to the difference of the variance when the machine is on versus when it's off, as well as this scaling of the average heat current, where we see that the efficiency is then the efficiency of our measurement setup, which in this case is about 10%. And notably, the results do indeed coincide with predictions, although there are, of course, a little bit more noise in than the average heat current. We can then use these 2 things in order to just plot the TUR. And I also here plot the bound of 2, and we see that, yeah, it coincides quite well. So all in all, we have then measured the average heat current, fluctuations of said current, which we used to an okay degree determine the TUR. So summary and outlook of things. We have then built a quantum thermal machine on a superconducting chip, showed that it can operate as a thermal machine by measuring the influx of photons into the cold bath. We've then measured the moments of power in order to then determine the average current as well as the noise of said current. Of course, as you see here, the signal-to-noise ratio of our noise measurement is still not to our complete liking. So in order to get a better estimate of the TUR, we recently installed a quantum limited amplifier in order to hopefully then improve the quality of these measurements, in order for us to then go into a regime where we theoretically would actually expect to see a violation of the TUR with this device. So yeah, with that said, I would like to thank you, and if there are any questions, I would be happy to answer.
Time for one quick question.
So the violation here is because of the coherent system?
Yes, that is correct. Yes, that is correct. So both the dephasing channel here and the decay are purely incoherent, and the only coherence that we find is indeed this coherent drive from 0 to A. Thank you.
Since that was a quick question, any other last question? Normally the chair would ask a question, but I was involved in this work, so I don't think I have any questions. So let's thank Simon again for a really nice talk. And for the next speaker come up, please.